All right, hello, Dr. Locke here, going to record projectile motion. This is problem number 3 for the pre-assessment. We're just going to kind of briefly cover it, hopefully briefly. We'll definitely cover it. All right. Pen here. Good deal. Hopefully everyone can see it. Okay, so what's the first thing we need to do? Read, all right? And we're going to find our, we can either go ahead and draw a picture or do our knowns and unknowns. So, K/U is unknowns and unknowns. So, get the sheet here. So problem number 3, someone want to read it aloud or let me read it? Let me read it since I'm on camera. Okay. So projectiles launch at 25 degrees to the horizontal at an initial speed of 10 meters per second. There is no propulsion on the projectile, neglecting drag. How long will it take to reach peak altitude? How high will it go? And then now how far horizontally will the projectile travel? So the main thing that's different between this problem and the last one, this is not being fired straight up in the air. So the rockets that we're going to shoot, we'll shoot them straight in the air. But when you're going to calculate the straw rocket stuff that we're going to do later, we'll be shooting them at an angle. We won't be shooting them straight up and down. Doesn't make sense unless the target happens to be where you're standing, where the projectile is starting to be launched. So again, we have a projectile, but now this projectile right here is being launched at approximately, well, it says 25 degrees, right? So here I've got the ground. I don't want to do dotted lines with the ground. The ground's solid. But so that's the ground. And I'm approximating the angle there by, it's not quite 45 degrees, it's not halfway, it's a little closer to the ground by 20 degrees. So that's one of our knowns, 25 degrees from horizon.
About 10 meters per second.
Right? So I think we're going to label that one theta. Back in the frame, theta. And then we're going to look at V initial, 10 meters per second. So one thing we didn't talk about in the last problem, but we can bring it up now, is when you're firing this thing straight up in the air, you have really the initial velocity is all in what direction?
Up 90 degrees.
So what direction is that in terms of our coordinate system? This is, think algebra, your graph. This would be what axis? X, and this would be Y axis. And so what degree angle, by the way, is this right here? 90. And if you were to use your calculator and you're in degrees, and you were to do what trig function would be the Y direction? Okay, so we need to make sure we get this. All right, so if this is theta, right? And this is Y, and this is X, sine, cosine, right? We knew hypotenuse is in there. That's this one. That's the hypotenuse. Which one is associated with that side? Which is what side?
So the
Opposite. Opposite. Which one's the sign go with? Opposite or adjacent? Opposite. So if I'm looking at Y direction, and isn't that what I gave you with that the additional formulas that you need for this?
V in the y direction is V initial times sine of
Yeah,
theta.
so V initial sub y is equal to VI, V initial, so that's in the y direction, times sine of theta. And so when we were looking at straight up, what is the sine of 90? Jose's answering all that. Sine of 90, if you use your calculator in degrees, sine of 90 is 1. The cosine of 90, that's the adjacent part. So if I'm looking at the x direction, the cosine of 90 is equal to 0. He's already had this class, he's memorized it, he's done it a lot. For those of you, but verify it, cosine of 90. For those calculators, you have to type in 90 and then hit cosine. But isn't it 0? So in other words, there is 0% in the x direction and 100% in the y direction if I'm shooting it straight up. So far so good? Y'all understand? So this is where trig ratios come in. In the x direction here, v sub I sub x, in the x direction, that is going to be v initial times cosine of theta. Now, which direction am I mostly aimed at, by the way? Am I aimed mostly in the x direction or mostly in the y direction? With 25 degrees.
Maybe X.
Yeah, mostly aimed in this direction. So it's not gonna, so theoretically, I would think the number in the x direction is gonna be a bit bigger than in the y direction. And by the way, that's gonna be true because there are actually two triangles I'm gonna draw here. We'll draw those in a second. But there's a y component going up here, v sub y, v initial sub y. Let me write that a little more carefully. V initial y is equal to vi times the sine of theta. And so if I know that I have these two numbers, I can actually get those two equations done pretty quick. So y'all catch me on that? So I know the velocity in the x direction and the velocity in the y direction pretty fast if I plug in, what, 10 here times cosine of 25. So this is initial velocity in the x direction in meters per second, because that's what that is up there. So what is that going to equal? 9? Can someone else verify that before I write it on the board and make it permanent?
Yeah.
What about in the y direction? Sine of 25. So that's 10 times sine of 25.
4.23.
Let's just keep with a tenth maybe, but I mean, 4.2, we'll probably get closer to the right answer if we use 100. I guess we'll do 3 since we did 9.06, but we could do 9.1 here and 4.2 here. But so which one's bigger? X direction, isn't that what we said? You're kind of aimed out more than you're aimed up. So far so good? So that's my v sub I sub y. My initial velocity in the y direction is 4.23 meters per second, and the v sub I sub x, the velocity in the x direction, is 9.06 meters per second. Okay? Now that was a lot. We covered quite a bit of ground there, but what's going to happen with this? What shape is this going to take when we actually launch that? Not a triangle, because it won't actually have a corner, but I will draw a triangle up here to go along with it. It's not a half circle, it's another thing. An arc, but what would we call that? Projectile motion actually follows this particular curve.
An ellipse.
So it's a parabola. It's a parabola. And if you look up what a projectile motion, it usually, you remember the ax squared plus bx plus c, right? You ever graph that, y equals? The thing though is if A is positive, it's going to go look like this. If A is greater than 0. If A is less than 0, it's going to go down. Okay? And where it crosses the x-axis, we usually call those our roots. So how many of you covered this in Algebra 1 already? You already talked about parabolas and all that stuff? Been a long time. So this is the practical application of this. Because this right here would be my 0 distance. This is my launching pad. And out here would be my other root. So I've come up with some equation where 0 is one of my roots and the other one's going to be some positive thing. Now if you're elevated off the ground, my 0 could be negative. It would actually be behind where my launch pad is if I got my launch pad up here and I got my ground over here. So this is going to be a parabola. And what's interesting is we still have kind of a peak height here, right? And you notice where I drew that? It's in the middle, right? Which means that I'm going to have initial velocity x going in this direction here. And I have initial velocity going in the y direction up. That initial velocity in the y direction, that 4.23 meters per second here, that's going to determine how far up in the air it's going to go. And then it's going to go up and then it's going to come back down. And what's the V final going to be right here at this height?
0. Well, V final in the y direction is 0.
In the y direction, it's going to be 0 meters per second. We don't know what it's going to be in the x direction.
Constant.
But this is the other thing. Do we have anything working against us in this problem? Do we have any forces working against us in the y direction? Going up. What do we have working against us in the y direction going up? If I throw something up, why does it come back down every time? All of it. Yeah. I have acceleration due to gravity. I have gravity is that A that's going down, negative 9.81 meters per second squared. I do not have anything in the x direction unless we had wind.
That says neglect drag.
It says neglect drag. Guess what? We've got nothing in the x direction slowing it down. So guess what V final in the x direction is?
9.06 meters per second.
By the way, that's going to help us with our distance, right? Because guess what? Our distance, let's just think about dx for a second. Distance is equal to what? What's the formula? What's the easiest formula there? Distance equals what times what?
V final squared minus V initial squared over 2a.
That's the more difficult of the equations.
Oh.
What's the easiest equation there?
V initial plus V final over 2 times time.
Which is what? What's that called?
The total or average
Where I'm
velocity.
adding them two together and then I'm dividing by 2, right?
Average
It's
velocity.
the average rate, average velocity. So we already covered that ground, right? Do we have an average velocity? Well, in the x direction, it's super easy. Because 9.06 plus 9.06 divided by 2 is going to be what?
9.06.
Yeah. The problem is we don't have time yet. Right? Keep this in mind because when we shoot the straw rocket, we're going to have this competition. I'm going to set a bullseye out a certain distance away. And what I want you to do is I want you to use math to help you approximate how close you're going to get there. I don't want you to use the guess and check method. I want you to calculate before you actually shoot. Because when I set the bullseye out, I'm not going to let you practice shoot. You get 3 chances to hit it. So you have to calculate, and then you have 3 opportunities. So, and the first one to get it, so if your team can get it on the first shot, hits the paper, hits the bullseye, then the other team has to either hit the paper or the bullseye or they lose. Okay? Follow me? All right. That's what I want to build up to. So I want you to calculate this type of thing, and I'll give you the distance, but I'm not going to set the bullseye out until y'all are ready to shoot. You're going to calculate this. So a lot of equations up here, but essentially this distance formula is something that you're familiar with since middle school. Average rate times time. We figure out the v, the initial velocity in the x direction. Nothing's working against this. So does that make sense? So there's no guesswork there, right? It's the y direction, and how long is this going to stay in the air? That's the question. And so we need to solve for time, only knowing a couple of things here, right? We know v final y. We know v initial y. What else do we need in order to be able to figure out one of the time constraints here? Is there an equation where if I know v final in the y direction, I know v initial in the, that I can only need acceleration due to gravity, which is that, so that I can solve for t? Is there an equation out there somewhere that we would possibly use? No. Anyone? So do you see what I'm modeling for you? I am modeling how to figure out which equation. You have 4 choices, right? Try not to bump the table. It's making my video go wonky. Just relax. And don't hurt yourself either. You have 4 equations. Actually, we had 6 because we included the vi sub x and the vi sub y in there. Those were pretty easy to figure out. So you have 4 basic kinematic equations. And I just told you, I know v final, I know v initial, and I know the acceleration due to gravity. Which one of those 4 do I can solve for time now? Yeah, and if I were numbering that, 1, 2, 3, 4 would be number 3, lower left corner. V final equals V initial plus AT. Now, let me tell you how that makes sense, right? The V final, if I know what the initial velocity is, and I happen to know the acceleration and the amount of time I'm applying to that acceleration, I am multiplying meters per second squared times seconds, right? When I do that, what cancels out? One of those seconds. And this is already meters per second, right? So when I add meters per second plus acceleration, if I just had acceleration, I couldn't combine those 2. But because I have a time component, I can do that, and I can now add meters per second plus meters per second to get meters per second. So you see how the equation is set up, and it looks like it's a bunch of different things, but they're actually related. And once I cancel something out, it's awesome. Let's plug stuff in from over there. So what is our V final? It's in the y direction.
0.
Meters per second, right? Oh, should we solve for t? Should we? Let's do that first. I don't want to cheat you on that part. So t is going to equal. So I need to take vi over to that side. So it's going to be what? V final, which is already over on the left side, minus v initial. So I'm going to take that over there, and then dividing it by a. So let's do that. T equals 0 minus 4.23. I know that's meters per second. time is going to be in seconds, by the way. So this is going to be in meters per second, because both of these numbers are meters per second. And then acceleration due to gravity is negative. Ooh, that's good, because a negative and negative cancel out. I get positive seconds, because gravity is working against us. And what's going to be left when I divide meters per second by meters per second squared is seconds. So what is that? Negative 4.2 divided by 9.81? I'm thinking it's like half a second. 0, let's put a 0 in there, is what you said. It is a decimal, right? 0.43 seconds. Okay? Now, is that the time that I'm going to plug in here to get my distance all the way across?
No.
What? Why? Why would I do that? Nice. So when we go up t seconds, that's going to be 0.43 seconds. How long is it going to take for us to come back down?
Seconds.
So there are a couple of questions that we could ask ourselves at this point. So if we start off at 0 meters per second at the top again, coming back down, at what speed are we going to be hitting the Earth, instantaneously before it stops back to 0?
Negative.
Is that what we're going to be doing? Yeah. I mean, theoretically, I think you're hitting the Earth at the same speed that you start off with here. Goes up, comes back down, and we could verify that by checking it at some other point. But yeah. So we're going to multiply this time 2 to get 0.86 seconds. By the way, that's one of our answers, the time of peak. But when we travel this and then this again, going up and back down in that period of time, because we are actually traveling back down, right? We need to figure out what our distance in the x direction is, which is 9.06 meters per second times 0.86 seconds. We're left with meters. Around what, 8 meters?
Yeah, 7.79.
In the x direction. Is there anything left to answer on that problem? Do we need to figure out the peak height?
Yeah.
Okay. So how would we figure out the peak height here? What formula would we use?
V initial plus V final over 2 times time.
Well, let's solve it for dy, right? We already had it here for dx. So we're going to do what? dy instead of vf(x), v final x, plus v initial x. We're going to do I was thinking v and wrote d. V final y plus v initial y. And it doesn't matter which one you put in front of the other, because you're basically adding the two velocities, dividing it by 2, finding the average rate, and then we're going to multiply that by just the 0.43.
So 0 and 2.
So that's going to be what? 0 plus 4.23. So it's 4.23 divided by 2 times 0.43. So what's the height? What's the peak height?
0.91.
So dy, or height, is going to be 0.91 meters. Dx, and some people use like r for range, or x. So but dx and dy here, the distance in the x direction, distance in the y direction. So I'm leaving that kind of in those forms so that you can understand that we can use the distance formula in the y direction, distance formula in x direction. It's the same formula in terms of the average rate times time. You can find it other ways, but that should give us the right answer. And then we would try to check it. One way to check it is by running through those again, make sure that we didn't do any careless errors. Check with our neighbor, look at the key, hopefully the key is 100% right, and all that good stuff.